So apart from that, let's look at now the biomass or the biogas digester, and it can also be called the anaerobic digester. So this is mainly used to produce biogas by mainly fermenting organic compounds, like maybe, for example, we can have silage, we can have grass, we can have decaying matter. So we can have decaying matter. So as a result, it produces now the biogas gas that is used for domestic use. So mainly this biogas is formed when microorganisms feed on waste organic products, like for example, we have the animal waste and the cellulose which are found in the organic matter. So this process is mainly done in the absence of oxygen, whereby in biology, this one will be called anaerobic respiration. So it is mainly through this anaerobic respiration which leads to the decay of the organic products, thus producing now this biogas which is being used for the domestic use, like for cooking and also for running the machinery that the relevant machinery that it runs. So you see that biogas mainly contains about 65% of methane gas, so between 60 to 70%. So it contains between 60 to 70% of the methane gas, and the gas is mainly used for cooking because that is the primary function of biogas. It is mainly used for cooking. And below, as you can see, this is the diagram which summarizes how the biogas is formed at home. So biogas mainly is dug, so that chamber, the biogas chamber, or the fermenting chamber, is mainly dug underground, and then the organic products thrown inside for the bacteria to feed on those produce in order to produce the biogas. So after these organic products have been fed on and produce the biogas, so the sludge is removed out and then discarded or used as fertilizer. So the biogas, being lighter than air, is collected at the top side of the chamber, as you can see, and then it is stored in tanks for later use. So apart from that, let's look at now the physical properties of the alkanes. So in this table, as you can see, the table summarizes some of the physical properties of alkanes that we have, whereby it begins by saying that the first four members are gases, then the last 6 members, you can see the last 6 members are liquids. So you see that the melting point and the boiling point increases down the series with increase in the number of carbon atoms. So as the number of carbon atoms increases, the melting point also increases as well. If you look at the density, you see that the density also increases with the increase in the number of carbon atoms. So the density increases with increase in molecular mass of the hydrocarbon. It increases down the group. So also the viscosity, we see that viscosity increases as the number of carbon atoms increases. Or we can say that viscosity increases down the group from methane to decane, whereby the first 4 members are gases, then the last members are liquids. So we see that all of these alkanes, all of them, they are saturated hydrocarbons. So all of them are saturated hydrocarbons having a single bond. So that is the other characteristic. So you can also see that these gases are colorless and they are odorless. So they don't stain. So they are colorless and also they are odorless. So apart from that, we see that the atoms are held together. These atoms are held together by which force? By weak van der Waals forces of attraction. So the weak van der Waals forces of attraction are the ones which are holding these non-metals together in order to form that molecule. So apart from that, you can say that these gases are non-polar, meaning that they only dissolve in non-polar solvents. So what are polar solvents? So polar solvents, these are solvents which have a polarity. Polarity meaning that they have a positive and the negative terminal. Like for example, you see for water it has the positive and the negative terminal. So the breakdown of water, as you can see, we have the hydrogen which is positive, and then we have the OH, the hydroxyl, which is negative. So the alkanes cannot dissolve in such a polar solvent, having a positive and a negative. It cannot. They only dissolve in non-polar solvents. So non-polar, it means that they only dissolve in solvents which have only negative terminal or only the positive terminal. So they are non-polar solvents, and then they only dissolve in non-polar solvents. Rather, they are non-polar substances, and they only dissolve in non-polar solvents. And then about the density, we can say that they have a lower density than water. So water is much denser than the alkanes, the liquid alkanes. So water is much denser than them. So those are some of the physical properties that we have for the alkanes. And then for the chemical properties, we see that the chemical properties, they undergo substitution reaction. Yeah, they undergo substitution reaction. They don't produce soot. And then they don't discolorize bromine water, potassium permanganate, potassium dichromate. So they do not discolorize them. So apart from that, the properties, let's now look at the nomenclature. So the nomenclature of alkanes. So the nomenclature mainly refers to the naming of alkanes. So how is it possible for you to name the alkanes? How can you be able to name an alkane? If I've drawn for you a structure of alkane and then asked you, give the name of the alkane. So how do you name the different alkanes that we have? So first of all, we see that the name of the members of alkane must end with A, N, E. So the names must end with A, N, E. Like for example, the first member is meth. So this meth is the name of carbon number 1. But since it belongs to the alkane family, we give it the last term ANE. So it's meth and then alkane, so methane. So all the names of the members must end with ANE, whereby we see that methane is the simplest member of the alkane family, having a chemical formula of CH4. So as you can as you can look at this table, so this table summarizes the alkanes again. It summarizes them by giving them the designated number of the members, by giving them the absolute name of the members, by giving them the molecular formula. As you can see, we also have a closed formula, a closed structural formula, and an open structural formula. As well, you can see the skeletal structure of these elements. So each corner, every line represents 2 carbon atoms. So every line represents 2 carbon atoms for the structural or for the skeletal formula. So every line represents 2 carbon atoms, as you can see. So in the skeletal formula of the hydrocarbons, only bonds between carbon atoms are shown. So between the different atoms, they are not shown unless stated otherwise. But in the skeletal formula of hydrocarbons, the only bonds between carbon are the ones which are shown. Like for example, you can see these examples. We have hexane. So in hexane, take note of the numbers. So these numbers denote where the carbon atoms have fallen. For example, you can see for the hexane, you can see we only have 6 corners to represent the position of carbon atoms. We have 1 methylpentane. So take note of the longest carbon chain. We also have the others like 2,2-dimethyl butane. So take note of the corners and the longest carbon chain, because that is the most important. So the bonds are always drawn in a zigzag manner. That is for the skeletal structure. So the bonds are always drawn in a zigzag manner. One straight of a zigzag represents a covalent bond. And for a covalent bond to be formed, we must have 1 carbon on this side, 1 carbon on this side, and then 1 line to join. So that line represents a covalent bond. Each side of that covalent bond represents 2 carbon atoms. So apart from that, you see that a molecular formula shows the element present in the chemical formula. So a molecular formula shows the elements present in the chemical formula of this structure. Like for example, you can see that the molecular formula for methane, the molecular formula is CH4. That is the molecular formula. And then for the open structural formula is now, it's like you have opened the structure, 1 carbon, and then show the position of the hydrogen atoms. Apart from methane, we can look at the molecular formula of ethane, which is C2H6. That's the molecular formula. The closed structure is CH3, and then for the open structure, you now open and then show the position of hydrogens in the respective carbon atom that there is.